Welcome back, everyone. This is the second part of section 7.1. Actually, we didn't do it all the first section, which I might have said in class. I don't know. Got kind of a long section. So this is just a one-topic section, actually, pretty straightforward. It's how to solve a differential equation using Eulers Method. So Euler developed a method for solving differential equations as long as he had one solution. So I'm just going to walk you through. No proof on this one. It's just a method. It's a pretty common method. It's pretty straightforward. Probably will you need a calculator on some of the problems. Just kind of use your judgment on whether you think you need a calculator. The example I'm about to give you definitely needs a calculator. On the AP test, typically without a calculator, just very simple problems. Really nice, easy numbers to work with. So here's how this works. It's pretty straightforward. You start with a differential equation. Okay, you start with the derivative equals something in terms of x and y. It might just have y's in it, might just have x's in it, just like other problems. But we just call that like some function of x and y in essence. So the derivative equals something. All right, it's a little weird notation right there because of the f, because you see function. It just means that the derivative has x's and y's in it. Okay. So what we're going to do is we're going to approximate solutions. So we're going to approximate solutions to this differential equation, dy dx equals f of xy, for numbers in a certain interval. So we're going to have an initial solution. So our initial solution here is y of something equals something, y of 2 equals 4 or something like that. And then what we're going to do is we're going to find solutions in an interval. So if we're going to start at that point that we're given, and we're going to try to find the solution at some other point, b. Ultimately, we're looking for b, but we're going to find other solutions along the way because that's kind of the way this approximation works. It needs to kind of work its way from one point to another one. So the way you do it is you break up your interval from A to B, whatever those are. You're given these numbers, by the way. Don't worry about that. You're given these numbers. So we're going to break these numbers up into a bunch of subdivisions. And we're going to break them up into even subdivisions. And we're going to call the width of each one of those subdivisions h, kind of like the delta x. So in other words, if we're going from 2 to 4 and we want to do it in 2 steps, we're going to go one number at a time. Okay, so n would be the number of steps. And this would all be given to us in a problem. We're going to be given the initial point, which is your small a. You're going to be given the answer we're really looking for, which is at b, and we're going to be told to do it in a certain amount of subdivisions. Okay. So once we do that, we start off with our first solution. Now this is going to feel a little bit like Newton's method for finding the zeros, if you remember that one. It looks like this. I'll just kind of write it out. Newton's method was the next guess equals the old guess, I call it one, minus the function evaluated at the old guess divided by the derivative evaluated at the guess. It's going to feel a little bit like that. This was Newton's method for finding the zeros, which were just an approximation of a zero. It just kept reusing a number. This is a little bit different. These are actually solutions to this equation, and we're going to find solutions along the way from one point to another. Okay. So here's the real important thing. This is the formula that you need to know. The rest is going to be set up for us. Is that this is your new solution. This is the solution you started with, your old solution. H is like the delta x. And then we're going to put the old solution into the derivative. And again, I'm going to walk you through a problem. You'll see it. We're going to put the old solution into the derivative. And then each successive step, we get another solution. So the computed yk is the approximate solution at the next x. So I wouldn't worry too much. If you're writing anything down, it's what's inside that box is the most important thing for sure. Step by step, I'm going to walk you through an example right here. It should be pretty straightforward, I hope. The example is a little complicated. The numbers aren't super nice. I used a calculator to do some of it. You'll see as I go. All right, so here's the problem. The problem starts with a derivative, y prime equals 1 plus y minus x squared. What we're trying to do, here's the question right here. Find the solution when x equals 2.4. Okay, this would normally not be there. They just say find the solution x equals 2.4, and then they would tell you how many steps to take. All right. So we're starting at 1. That's why I put that there, just so you can see that. Okay. We're starting at 1. How do I know we're starting at 1? Because that's what's given to us in the problem is we have to have an initial solution in the first place. And we're going from 1 to 2.4. Okay, very, very straightforward. And we're going to find solutions along the way. The more solutions you find along the way, the better your approximation is going to be when you get to 2.4. If you do it in 2 steps, your approximation is not going to be quite as good. So the number of steps would always be given to you in a problem. So we're going to do 10 steps in this problem. We're not actually going to do all 10. Don't worry, it'll take forever. Typical problem is like 2 to 4 steps. On the AP test, typical problem is 2 steps. Very straightforward, very, very, very easy. All right, so here's how it works. Remember, my first solution is 1.59. So here's how it works. Is I take that 1.59. And I'm going to add that to my step size. The step size is 0.14. I got that 0.14, remember, because we have 10 steps. 10 steps, and we're going from 1 to 2.4, right? So we're going, our total distance we're going is 1.4, and we're doing it in 10 steps. So each step is 0.4. And then what I do is I multiply that by my derivative evaluated at my initial guess. So what you'll see me do on the next step is that, remember, my original guess was, my original solution was 1.59. So what you see me here doing is putting the 1 and 1.59 back up into that equation. So it's 1, oh, sorry, that's not the 1. It's 1 plus y minus x, 1.59 minus 1 squared. Multiply that by the 0.14, add it to the original solution, and I get 1.778734, which means I now have a new solution. But where is that solution is kind of the important step here. All right. And that solution is at 1.14 because I started at 1 and I went over a step size of 0.14. So this is my, what we would call my next solution. And I'm going to do this all the way to 2.4, 10 times. I'm not really going to do 10 times. Don't worry about it. I'll maybe show you one more here just to kind of walk you through the process. And now I have a new solution, right? So now the next solution is going to be take the new solution, the 1.77834, which is that old solution from right there, right? Add it to the step size times the function evaluated at that old solution. So now I have to take that 1.14, the 1.14 and the 1.77834 and put it back into my equation. So here's my old solution. Step size, 1 plus y minus x squared, back up to that one. And now I get a new solution, which is 1.975. But where is that new solution? Well, that new solution is at another 0.14 over is 1.28. So that's the process. You know, if I'd asked for the solution at 1.28, this would be the answer. I asked for 2.4. I would never make you do 10 steps. Don't worry. I just wanted to kind of walk you through it. One other thing really that comes up, and that's it, is let's say the initial solution is 1, 2, or whatever, and I want solution at x equals -2. So that means I'm going to the left. So notice the original problem I did, we were going from 1 to 2.4, right? But now I'm going from 1 to -2. That means my delta x or my h is a negative number, okay? Really, really important, okay? Otherwise, you're going to get the same answer in essence. Well, it wouldn't be the same answer, I guess, but it's just not right. So negative, if you're moving to the left, your h or your delta x needs to be a negative number. So you might see that in a couple of the problems. There's an example of this in the book too. It might even be the same one. You kind of want to walk through it. Again, it is a pretty easy process once you recognize it. And the numbers won't be this bad. Like I said, a lot of times these problems are non-calculator problems, so they just come out nice and easy. You're not punching the calculator too much. That's it for this one.